Hey, honors geometry students, welcome to your next lesson. In this video, we are going to be focusing on identifying the relationship between central angles, inscribed angles, and the arcs they intersect. So, what you have learned up to this point is you have learned a variety of vocabulary. But if you're right now like, oof, I don't know what vocabulary you're talking about, maybe pause this and go back and look at the video from last time, right? So you got a lot from some videos, and so you did learn actually some information about this already, but I want to show why it's true and go more in depth, right? But we're going to kind of start off with the premise of knowing what a central angle is and what the relationship between central angles and the arc they intercept is. To clarify, when I'm saying arc, an arc is a portion or a part of the circle, right? So a semicircle is half the circle, right? So, if I drew a diameter in here, I'm thinking about, okay, that's a semicircle, it's half a circle. I know we've worked with that. And this would be the arc that's intercepted. Oh, that's the arc that's intercepted by a 180-degree angle, right? If I want to talk about, so it's just a portion of the circumference. So if I had another circle, and remember you talked about major and minor arcs. So if I had, like, this could be an arc. So I could have an angle that intercepts, right? Like it chops off that arc right there. Right? So that's what I'm saying. It's almost like, it's like Pac-Man, right? And like, what does it eat? What's it eat? What's it eating? What's in its mouth? Okay. So we're going to talk about the relationship, and our focus is going to be on the measure. What do I mean by the measure? Right? Do I mean length? No, I don't mean length. When I'm saying measure, I mean the angle measure. So angle / arc measure. Right now, we know that to be degrees, right? So like 180 degrees is a measure, right? You're talking about, it's an angular measure, right? It's a circular measure is what I'm getting at, not linear. Okay, so let's see what we already know. So angle OAC, okay. So let's just think about some things we already know. So AOC, that angle is formed by two radii of this circle, right? AO is a radius and OC is a radius. We also know that the vertex of this angle is O, which is the center of the circle. This is what is known, and you might already know this, you might have said this first, as a central angle. Okay, it's a central angle, and this stuff will always be true. It will always be formed by two radii. And the vertex will always be at the center of the circle, right? That is what gets me a central angle. And you did learn about these, maybe you recall, when we learned about the unit circle, right? If you remember talking about the unit circle and we drew out the circle, this isn't very nice. And we said, oh, you're always going to start at the positive x-axis and you're rotating, and this is 30 degrees, right? We're really talking about a central angle. A central angle, the measure of a central angle is equal to the arc it intercepts. So if AOC is, let's say, 42 degrees, the measure of this arc is also 42 degrees. Remember, I'm not talking about length. So I could dilate this circle. I can make it really, really tiny or really, really big. And that angle measurement is going to stay the same. So I'm not talking about length. I'm talking about measure, degree measure right now. Okay. ABC is a little different, right? So like this is, let's see what we know about our vocab. It's formed by two chords, right? It's formed by two chords, but it's not just any angle formed by two chords, right? Like they intersect on the circle, right? Or on the circumference of the circle, right? Like AB and BC are two chords, and they intersect at point B, which is a point on the circle. Okay, so for this, the vertex is B, which is on the circle. And I'm going to do this a little different. I can't remember if this was in the last video, but I'm just going to tell you what the rule here is, and then we'll prove it, and we'll take a look at it a little bit closer in a moment. We'll show why it's true, or visually why it's true. Okay, so the measure of an inscribed angle is 1/2 the measure of the intercepted arc. All right, so I can do this both ways. I could give you the angle and tell you to find the arc. I could give you the arc and tell you to find the angle. Right, so we know that this arc is 42 degrees. Right, and we knew that this was the central angle that intercepts that arc. If I take a look at this other angle that I'm looking at, this inscribed angle that I found, doesn't that also intercept this arc? So if what I'm saying is true, and that the measure of this angle is half the measure of its intercepted arc, this angle should be 1/2 the measure of AC, or 1/2 of 42. So it's 21 degrees, right? And I'm just asking you to trust me right now. I'm telling you the rule, and then I'll show you why it's true soon. Okay? Okay. So these three right here are examples of central angles. The measure of the central angle is equal to the measure of the arc that's intercepted. And some of these should be fairly straightforward. Like we know that if you rotate halfway around a circle, it's 180 degrees. Well, you also know that a line is 180 degrees. Oh, same thing here. A quarter of the circle, you have a 90-degree central angle, 90-degree arc that's intercepted. So sometimes, like those of you that like using highlighters, this is your time. This angle must be at the center of the circle. If this, right, like I can confirm, and I'm like, oh yes, this is the center. It is. It has to be. If the arc and the angle are congruent, then it must have been a central angle. Pretty cool. Right? Or here, okay, here's a central angle. The arc that it intercepts is 50 degrees. Right? That's a minor arc. I could ask you to find the major arc too, right? The one that's all the way over here, the other part. This is 200 degrees. So this arc is also 200 degrees. Wait, this is not a central angle, right? I don't know where the center is. I do know that what's the measure of this arc? 160, right? So if I were to locate the center, by just what I'm telling you, this should be 160 degrees. But this isn't a central angle. This is an inscribed angle. So we do need to make sure we're paying attention to the types of angles. It might be neither, right? I might give you a circle, and it's like, well, right now I don't have enough information to figure that part of it out, right? So let's take a closer look at these inscribed angles. And let's look at I'm going to very loosely call it a proof. Will it let me? Okay. So there's a few different cases, and I'm just gonna show you how it works. So some of them I could put numbers in it, but I'm not going to. So hopefully you can see this. And you can see right here that I do have this angle X, if I were to extend this, is going to go through the center and it's going to intersect this purple arc, right? I'm just going to call it X. I'm going to show you, and you guys you're able to click on this, right? So, okay, there's a radius. I can connect it. There's the other radius. So my first case is going to be an inscribed angle where one of the chords is the, is the diameter, okay? So watch what's going to happen here. So I'm going to create a central angle that intercepts the same exact arc, right? And a central angle is formed by 2 radii. Cool. Now I'm going to swing this around. Do you see how I have actually 3 radii now? Right? So I actually just created another central angle over here too. So if this is X, this one down here also has to be X, doesn't it? Don't you have an isosceles triangle? So watch what happens though. I'm going to go ahead and take this angle, and maybe you have a recollection of doing constructions, drag it down here. Right, I've got those 2 angles. I'm going to move them. Let's confirm it. Okay, let's take it and plop. Take the other one. Plop. Whoa. Right? It took me 2x. This was x. This was 2x. This is half of the measure of this one right here. Pretty cool, right? Let's look at the next case. So this one, I have an inscribed angle. Neither chord is the diameter, right? So like, I still know that like if this is 80, this is 40, right? It's half the measure. I'm telling you that, but let's see how it's true. We still want to somehow get a central angle. Okay, so let's go ahead and let's draw in the diameter. Okay, there's my diameter. So it went right through X. Let's take it away and let's focus on this radius. Cool. So I can have that radius, I can have this radius over here, this radius over here. Okay, so I know that this whole purple angle was X. It's split over across 2 triangles right now, but I do know that it's X. Okay, so let's see. We're going to call this Y. And let's show you what happens. I'm gonna go ahead and take X and let's see what happens. And let's talk all of X and let's swing it down here and plop it, and then let's take another X. Whoa, it fits again. Right? So this whole thing was X, this was 2X. I was able to create that central angle. Let's look at one more case. Our third case is going to be created when we have an inscribed angle, but the other one crossed over. So when I drew that diameter in, it didn't bisect, but it cut the angle that I started with into parts, not in half, but into parts. Here, my angle is not, right? So it's like if I were to, and I will at some point, extend this angle, this is where it's going to intersect. Right, and that'll be my intercepted arc. So, still going to start by drawing that diameter. There's a radius. There's another radius, and let's swing this radius around to that spot. Back up for a second. And I'm going to draw my angle in. So I've got now this isosceles triangle, right? Formed by 2, it's a central angle. Call this Y. Let's draw one more in, right? Another isosceles triangle. There's a lot going on here, right? But I'm just trying to get a central angle that intercepts, and you have it now, right? Here's your central angle that intercepts the same arc that I was focused on. Okay, so now I'm going to go ahead and I'm going to take this angle that I started with, X. Let's see what happens. Woo. Right, swing it around, get it to fit. Swing it around. Whoa. Right? Pretty cool. So you've got to use the central angles to get there. So you're just seeing why it's true. It's my very informal idea of a proof, just so that you guys can visually see. And you have access to this if you want to go ahead and click on it and play around with it. Okay, so let's summarize what we just learned. Theorem number 1, we're going to talk about a few. The measure of an inscribed angle is 1/2, or you can write the word half, the measure of its intercepted arc. This theorem will also work for a tangent and a chord, right? Like we just looked at it when it was 2 chords. It could also be 2 secants, right? A chord is a portion of a secant. But I could have it where the 2 secants intersect on the circle. I could have it where here's a tangent. That wasn't very good. And here's a chord, right? It's a little silly, but like this angle is like treated like an inscribed angle, as long as the vertex is on the circle. So our key pieces are we're looking at where's the vertex. If the vertex is on the circle, it equals to, it is referred to as an inscribed angle, and it is 1/2 the central angle that intercepts the same arc. So you got to be mindful of that, right? If there's a lot going on, like you got to really narrow in your focus and see what you do now. So in these 2 quick examples, we're going to find the measure of angle BAC and the measure of arc FE. That's what the little m means. So BAC, oh, well, I was just told that, and I saw it for myself with that neat GeoGebra applet, that this is an inscribed angle. The vertex is on the circle. It intercepts this arc, which neat, I know is 60. So to find the measure of angle BAC, I'm going to do 60 divided by 2 and get 30. So that angle is 30 degrees. What about the measure of arc FE? So let's find FE. That's over here. Oh, whoa, where that starts and ends, I see chords. When I follow them out, oh my gosh, those 2 chords intercept on the circle. So it's inscribed. So that means in order to get from there to this arc, I have to do 70 times 2, which gives me 140 degrees. How about the second one? Now I'm going to find the measure of angle ACD and ADC. ACD is right here. Let's see. Vertex on the circle. Let's follow it out. And it intercepts this arc, which, oh, sweet, I know it. So I'm going to go ahead and 70 divided by 2 gives me 35 degrees. Huh, do I know anything else? They didn't tell me anything else, but I do actually know this, don't I? I think I do. Isn't that half a circle? Isn't that 180 degrees? Okay, so why does that help me? Well, this angle, ADC, but if I just say how that extends, it's like eating this arc, right? It's intercepting that arc. It's inscribed because the vertex is on the circle. So 180 divided by 2. Oh my gosh, I get 90 degrees. Hey, they didn't ask me this, but I totally could have figured out this angle. I also could have figured out this arc, right? Oh, I now know that this is 90. 90 and 35 gives me 125. Triangle sum theorem, guys. 125. That is that 55 degrees. And then 55 times 2, I can solve this whole triangle, this whole circle, 110, which makes sense. 110 and 70 is 180. It's a semicircle. Whoa, real cool. Well, wasn't that just an angle inscribed in a semicircle? That's what I had here, right? If I gave you this one, which now I'm realizing is basically the same question, okay, this angle is inscribed in a semicircle. If I know that, it is a right angle. I don't need to worry about trying to figure out all these other pieces. I want to know that an angle inscribed in a semicircle, an angle that, when I'm saying inscribed, intercepts a 180-degree arc. Right? So that's my second theorem. An angle inscribed in a semicircle is a 90-degree angle, or a right angle. Well, that's pretty cool. I know. Oh, check this out. Cool. Intercepts a semicircle. So angle, the measure of angle WZY equals 90 degrees. Well, then I can find A, right? I can do algebra. Minus 20, 5A equals 70. Divide by 5. And what is that, 14? I hope that's right. I think it is. Right? Pretty cool. Well, let's take it even a step further and let's think about this one. What can you tell me about the measure of angle TRU okay, that's inscribed, and TSU, also inscribed, and their intercepted arc? Wait a minute. Does anyone else see what I'm seeing? Don't they both intercept this arc? Don't they? Aren't they both inscribed angles and intercept the same arc? What does that mean? If this arc is, I don't know, 32 degrees, wouldn't this one just be half of that? 16? But wouldn't this one also be half of that? Also 16? So two angles that are inscribed, two inscribed angles intercept the same arc, aren't they? There's a word for that. Congruent? Aren't they congruent? Right? I'm going to write that a little bit more formal. If two angles intercept, if two inscribed angles intercept the same arc, they are congruent. Right? That's my third theorem. So like, check this out. So I know this angle and this angle. Whoa, whoa. I don't want a highlighter. That's a or laser pointer. Right? These two angles are both inscribed angles. And let's see what they intercept. This one intercepts that arc. This one also intercepts that arc. So I know they're congruent. 3b has to equal to 5b minus 7. Okay. Minus 2b equals negative 7. B equals 7 halves. Or maybe you're saying 3.5. Couldn't I go a step further? And I mean, I guess I didn't even read the question. I found the value of B. It's asking me for the measure of arc LM. Well, let me plug it back in. Do I need to plug it back into both of them? Not necessarily. It's a good way to check my work, but I certainly don't have to. I get 21 halves, or I believe that's 10.5. And let's just make sure. If I did 7 halves times 5 minus 7, I get 35 halves minus 14 halves, which is absolutely 21 halves, which is also 10.5. So good. That's a good way for me to confirm. I plugged into both to make sure that I did this algebra right. Okay, so then I got the measure of the angle, the inscribed angle. But I know this is 10.5. The inscribed angle is half the arc it intercepts. So let's double it. 10.5 times 2 to get 21 degrees. So this arc is 21 degrees. Okay, so let's do some practice. And this is where I would encourage you to pause the video, try it on your own, and then listen to me to go over it. So hopefully you've had an opportunity to try. So our goal here is to find the measure of angle IHJ, that's this angle, as well as the measure of arc GH, that's this arc. They actually don't really rely on each other, do they? GH I can see is intercepted by this angle that I'm given, this inscribed angle. I know it's inscribed, make sure you check that. So I can just go ahead and say, well, 20 times 2. So that's going to be 40 degrees. This arc angle right here is formed by two chords. The vertex is on the circle, and it intercepts this 90-degree arc. So 90 divided by 2, the angle is half the arc, is 45 degrees. Okay. So sometimes these can get messy, and they're like, for those of you that like puzzles, like these are like puzzles. You got to figure out what should I start with. Sometimes things impact each other. Okay, so I'm going to find y here. Well, this is interesting. I'm told a few things. I'm told that these two sides, these two chords are congruent. So this also must be 4y minus 7, right? What's this angle? Well, it's an inscribed angle, and it intercepts a semicircle. Didn't we just learn about that? So this is 90 degrees. So that means that these two angles must be 45, right? 180 minus 90, right? Minus this 90 is 90. Divide it by 2 because they're both congruent. That was why it's important for me to pay attention to the fact that it was isosceles. I get 45 degrees. Okay, well then let's solve it. 4y minus 7 equals 45. Go ahead and add 7. And I get 52. Divide by 4 and I get 13, I think. Okay, so y is 13. I can totally plug that back in to check it. Right, and when I do 4 times 13 minus 7, I do get 45. Amazing. Let's go ahead and do this last one. And again, pause the video, try it, and let's come back together and chat about it. Okay, so hopefully you tried it. The measure of angle DAE and ADC. DAE is right here. It's an inscribed angle. It intercepts this arc that I'm given. So I can go ahead and do 76 divided by 2. And I get, is that 38 degrees? For ADC, that's an arc. A, which way do I go? I have to go from A and then to D and then all the way to C. So I want to go all of this, right? I knew that that's going to be, that's a major arc. So it's going to be greater than 180 degrees. So let's think. I know that this is 100, and I guess there's different ones. No. I know that this is 135, and doesn't it actually intercept that arc? The angle is half the arc. So the arc divided by 2, or times 1/2, is going to equal to 135. So let me just double it. The arc is going to be 135 times 2. What is that, 270? 270 degrees. Okay. So in this lesson, we identified the relationship between central angles and inscribed angles, and we looked at why that exists, and we proved it a little bit through those GeoGebra applets. And we looked at a little bit of an introduction of like how we would be using this and how some algebra comes into this, and really like the puzzle that we're trying to solve. We also talked a little bit about the definitions, and remember that when I'm saying the relationship and I'm talking about measure, right now we're talking about degree measure. Right, and keep that in mind as you're going forward through this, and just paying attention to what actually intersects. So it suggests, again, like use highlighters, use different colors. If you're on Cami, different things, just pull out, like they have a highlighter, I think, just to kind of color code. And those of you that are very into puzzles, this kind of fits in that arena. So this was just an introduction. We'll definitely have an opportunity to do more practice together and some more rigorous practice together, but we'll save that for our next class period. Your job now is to just make sure that your homework is done and you've done some practice and you're prepared for when we see you soon in class. Thanks everyone for watching.